Hello everyone. In this session, I'd like to explain the derivatives of a transform. Laplace transform is a function of s. So we'd like to find out the derivative with respect to s, df over ds. We substitute the definition of the Laplace transform integrals over the t from the 0 to the infinities exponential minus st lower case of the f as a function of t. And we'd like to find out the derivative with respect to s. So we'd like to move these derivatives inside of the integrals. Then we change to the partial derivative. Exponential st is a function of s. Then we could perform the derivative with respect to s to the exponential minus st to produce a minus t. So except this negative sign, other part of the equation is exactly equal to the Laplace transform of the tf. So we could write under it's equal to the negative Laplace transform of the tf. So Laplace transform of the tf is equal to the minus the derivative of the Laplace transform with respect to s. Okay, we could obtain these formulas. So if we change the f to the g, actually we could also write under Laplace transform the t gt is equal to the minus derivative with respect to s, Laplace transform of the capital G. Then we'd like to find out the Laplace transform of the t square f. Then this is gonna be equal to t times tf. Then if we consider that tf is equal to gt, then it becomes minus dds times Laplace transform of the g. Write under these equations using these formulas. Again, we can apply the Laplace transform of the tf using these formulas. Apply to this ones. Then this is gonna be equal to this one. So by multiplying the minus 1 twice, it becomes a 1. So it becomes the second derivative of Laplace transform of the f with respect to s. So if we apply the one more times, you might easily find it's a t cube ft. It's a minus 1. It's gonna be cube. Third derivatives fs. Then we'd like to show the transform of the integrals. Before showing the transform of integrals, I'd like to introduce a new term of the convolutions. This is a definition of the convolutions. The convolution of f and g is defined with the integrals f tau and g t minus tau and the integral with respect to tau's, and the lower limit is 0 and the upper limit is t. This is the definition of the convolution. So if you want to find out the convolution of the exponential t cosine t, for example, using the definitions, you can express the exponential tau cosine t minus tau d tau, and changing from 0 to the t. So I'd like to show you this convolution. And also I'd like to show you how to calculate the convolution. Then we can use the integration by part. It becomes exponential tau sine t minus tau. Tau is changing from 0 to the tau equal t. Plus tau is changing from 0 to the t. Exponential tau sine t minus tau d tau. We'd like to substitute tau equal t. Then sine 0 equals 0. Then we'd like to substitute tau equals 0. It becomes minus minus becomes sine t. And then one more time, so we'd like to perform the integration by part to the second terms. So it becomes exponential tau cosine t minus tau. Tau equals 0, tau equals t. Minus tau equals 0, tau equals t. Exponential tau, cosine t minus tau, t tau. Again, you can substitute tau equals t. So cosine 0 is a 1. So first term is a sine t plus exponential t's. You substitute tau equals 0, it becomes minus cosine t minus 0 to the t exponential tau cosine t minus tau d tau. Then if you look at this form of the equations, this is exactly equal to this expressions. You might find out this should be equal to the convolutions. So by moving this term to the left hand side, it becomes exponential convolutions cosine t equal sine t minus cosine t plus exponential t. Then finally we obtain the convolutions. Cosine t is 1 over 2 sine t minus cosine t plus exponential t. Okay, so I showed how to calculate the convolutions. Then I'd like to show the Laplace transform of the convolutions. Convolution is expressed with the integrals. So this corresponds to the Laplace transform of integrals. If you consider the Laplace transform of the convolutions, actually it's gonna equal to the product of the Laplace transform of the each functions. So I'd like to show you these formulas. So we start from the right hand side and it's change it to the left hand side. So right hand side is the Laplace transform of the f and the g. So using the definition of the Laplace transform, this corresponds to the fs. This corresponds to the gs. Using the definition of a Laplace transform, then we combine these two integrals into the double integrals as a function and the p and q's. Then we'd like to change a variable from the q to the r using these equations. R equal p plus q. Then this part becomes r. If you calculate Jacobians, and Jacobian becomes ones, so it becomes dp dq is equal to dp dr because the Jacobian is ones. Then we'd like to change the q. Q equal r minus p. We move to the next lines. So p is changing from 0 to the infinities, but r is changing from the p to the infinities. Exponential minus sr, fp, and g is a function of the r minus p. Then we'd like to consider this integral of the dp dr. To consider the regions of these integrals, we draw the figures. Vertical line is a p, and the horizontal line is a r. So p is changing from the 0 to the infinities, and the r is changing from the p to the infinities. So if you draw the lines of the p equal r is changing from the p to the infinities. So this is following from the starting at this point is moving to the right, and the p is changing. So you can draw the many lines, and then finally it's covered these regions. And then we have another way to perform the integrals using a different arrows of the integrals. So in this case, r is changing from the 0 to the infinities. these lines. And the p is changing from the 0 to the r. So following this one. So you can draw the many arrows to cover this regions. This region. So p is changing from the 0 to the r. The integrals. So we change the term of the integrals, double integrals. So in the green case, integral with respect to r first, and then integral with respect to p later. And in the case of the red double integrals, integral with respect to p first, and the integral with respect to r later. If you look at these expressions, except the exponential SR, this integral surrounded by the blue lines is equal to the convolution of the FG. So if you look at this expression, this is exactly equal to the Laplace transform of the convolutions. So finally, we proved Laplace transform of the convolution is exactly equal to the product of the Laplace transforms of each functions. We proved these formulas. Okay, in this session, I introduced the derivative of a Laplace transform and the Laplace transform of integrals. Okay, this is the end of this session.